next talk will be by Ruth Urner from York University on robustness. Should not get off with that.
Okay, yeah, thank you. Yeah, and the first thing I want to say is the work that I'm presenting today was the work of my master's student, Sadia Chaudhuri, and she was hoping to present it today here. Unfortunately, she couldn't travel. I'm hoping she is somewhere on Zoom now. So I last minute jumped in to give this presentation. I was really hoping that I could meet up and actually celebrate her graduation also. That was during the pandemic. Okay, so we're looking at a classification. So here's a standard binary classification setting. So we have positive and negative examples, right? So say some images with a person or not a person. In learning theory, we usually assume that the data is generated, or we model that the data generation is a probability distribution. The learner gets a sample. The goal is to output a classifier. The goal is to output a classifier actually of low risk, meaning that if we get a new example, then the classification should be correct. Right? That's the usual setup. And then learning theorists like to analyze this through this framework called PAC learning. VC theory then characterizes learnability in binary classification. But that doesn't capture the phenomenon of adversarial examples. So adversarial examples kind of became a concern. I mean, by now I think it's almost a decade ago. The phenomenon was that there were these deep neural networks that were performing really, really well on computer vision applications, winning all the competitions. But then it turned out that very small perturbations can actually make these networks misclassify badly. So often just flipping a pixel or adding some additive noise that for a human would actually not change the label of an image, flip the prediction of these otherwise really successful neural networks. And that, of course, is a huge security robustness concern. So then, of course, there was kind of a whole industry, or that by now there's a whole industry aiming to make neural networks more robust. On the learning theory side, there's a whole industry analyzing learning under a robust rather than just a binary classification loss. So on the practical side, often data is, I mean, there are different approaches. The pre-processing approaches where the data is often augmented. Adversarial examples are added at training time with the goal or with the aim that then the learned predictor will actually already get those perturbations correct. And there are modifications to the optimization in processing, aiming again at the adding at optimization time adversarial examples, or the post-processing methods, smoothing a trained classifier out afterwards. And on the statistical learning theory side, there are various studies that have looked at how does this aim of training with respect to an adversarial loss, how does it affect computational complexity? How does it affect sample complexity? This type of question. So let's briefly look at how do we model the adversarial loss, or how is the adversarial loss traditionally modeled? So here we have this binary classification setup. So the binary loss, if there is an example that the classifier that has a different label than what the classifier assigns, we assign binary loss, binary classification loss. Adversarial loss, we also assign loss when there is a small perturbation. So if there's a small perturbation to an input example X, such that the classifier assigns a different label at this point, right? So here, if this red point here is our X, there could be an X prime that sits here across the decision boundary, where the classifier assigns a different label, therefore we would assign adversarial loss. Right, so we can, and the adversarial loss, of course, also still penalizes misclassifications. Right, so we assign adversarial loss both if there's a misclassification and if we're close to the decision boundary, meaning if a point falls into the margin area of the classifier. Right, so a bit more formally here. This is again just saying either if we're making a mistake or a point falls into the margin area, then we're assigning adversarial loss. So that's how adversarial loss has mostly been modeled, or how this phenomenon of aiming for adversarial robustness has mostly been modeled. Right, and in this talk, I want to propose an alternative way. That's maybe the outlook here, right? To propose an alternative way, or ask the question: is this actually modeling what we were intending to model? Thinking about these adversarial perturbations, these small pixel flips in images that for a human don't change the label, but where a trained network misclassifies. Right. So with this notion of adversarial loss, we've seen studies showing really drastic gaps in sample complexity, gaps in computational complexity. It's also been argued that robustness is in conflict with accuracy. So I will want to focus actually on this last point in this talk, and argue that robustness should not be at odds with accuracy, right? So what we're proposing in this work is to reframe the adversarial loss to avoid this phenomenon of conflicts with accuracy. Right, so why is there conflict with accuracy? This is a very simple or very simplistic actually example that shows this, right? So here on the left side, so if we look at a very simple distribution, we have 2 points, there's a little bit, so the mass is sitting in 2 points or 2 small areas with 2 different labels. If and a classifier classifies both areas correctly, but both areas would actually fall into the margin area, then in this case we have robust loss 1, where such a classifier that misclassifies all the points, but keeps a little bit more of a distance to the data generating distribution, actually receives as adversarial loss 0.5. So in the classifier here on the right hand side would actually be better in terms of adversarial loss. Right, so if we choose the robustness parameter a little bit too large, then the optimal classifier with respect to the adversarial loss is not doing what we would want it to do in terms of classification correctness. Right, so on the other hand side, what one can show is that on separable distributions, right, so if we have a clear distance between, say, positive and negative examples, then there exists a robustness radius that such that the optimal robust classifier is actually also in line with the optimal binary classification classifier. So in this work, when we went a bit further, we analyzed kind of how these this phenomenon actually also relates to the noise in the data generating distribution. We introduced this notion of a margin rate that measures, as a function of the radius, measures the mass of distribution, assigns to the margin area. So we can kind of also show that one can always, as a function of the margin rate, one can choose a robustness parameter such that robust optimal and binary optimal coincide, but also if we have, if it's a little bit too large, right? So then if we have some noise, if we choose the robustness parameter that's a little bit too large, then the optimal binary and the optimal adversarial predictor can define half of the space, right? So they can just be very drastically different. So here's just to summarize. So base optimal with respect to binary loss and adversarial loss can differ vastly. And what that means is that training with respect to the adversarial loss is inconsistent with respect to the binary loss. If we train, or if we have a method that is statistically consistent with respect to the adversarial loss, it will converge potentially to a predictor that is on half of the space different to what we would actually like to converge to in terms of binary classification loss. Right, so in that sense, robust loss minimization can hurt accuracy. Right, so then the question we were asking here, or the question Sally was asking in her master's work is this notion of loss actually capturing what we intended it to capture. So if we look at such a picture here, again, this is just a very simplistic distribution on 4 points or 4 areas. So the idea here is to say, well, sometimes this distribution is perfectly separable, of course, but sometimes the margin is locally different in different areas of the space. Right here we have large margin, here we have smaller margin. This orange line is a robust optimal, but maybe intuitively we really would prefer behavior like the green line, right? Really, what we would like to see is that the trained classifier is everywhere in the space as robust as it can be, right? So if there are areas of the space where the robustness can actually be much larger, then wouldn't we actually want a trained classifier to behave like this? Right, so this led us to aim to formalize this notion of localized robustness requirement. Right, so the question is, how do we formalize this? So we noticed, so we would like to actually, the robust loss, we would like it to be in line with the underlying data generating distribution with a base classifier. Base classifier is not always uniquely defined. So first thing we did here is we defined a notion of what we call the margin canonical base predictor. Base predictor is not uniquely defined in areas where there's no support of the distribution. And I actually think that this phenomenon of the distribution not filling the whole space might actually be what is causing these phenomena of adversarial examples. Right, so if we imagine in some image classification task, the data is sitting on some lower dimensional manifold, the network can do really well by cutting very close, having a decision boundary that cuts very close to the manifold, is correct everywhere on the manifold, but that gets us to these adversarial perturbations where the network has strange phenomena. So we introduce this notion of a margin canonical base that essentially says everywhere where the base optimal is not uniquely defined, we define it in terms of a nearest neighbor. So here in this case, the black line is a margin canonical base predictor that aims to be everywhere as far as possible from the two labels. So using this notion of margin canonical base predictor, we then say, well, we want adversarial loss, or we want the loss function to assign loss, either if there's a misclassification, of course, or if the classifier is not as robust as the margin canonical base, right? So we want the trained classifier to be everywhere as robust as the margin canonical base predictor. Potential issue with this is, or one could ask, why hasn't this been defined this way initially? This is not a loss function in the sense of loss function that we usually use in statistical learning. Usually we would want a loss function to be a function of a classifier and say an input-output in classification. This loss actually depends on the underlying distribution, right? So this is not, one could say, well, on one example, HXY, and one predictor and an example, we can actually we don't know what this loss would be. But we can actually, on a data set, we can have a very natural version of this loss, right? So we can, if we are given a training sample, say, we can use this loss function on the uniform distribution over the training points. 5 minutes, okay, that's good. So what this means is that for every data point, we can look at what is the distance to its closest point with a different label? And we can set the radius, the intended robustness radius, to half this distance, right? And if a classifier actually cuts within this ball that is defined by half the distance to a point with a different label, then we would assign empirical adaptive robust loss, right? So there is actually, even though this is not a pointwise defined loss function in the traditional sense, there's a very natural version of this that can be applied to data sets. And then, right, so this is the definition, then the formal definition. And this also leads to a very natural data augmentation framework. So we can, now that we have this on a data set, this adaptive robustness radius, we can use this radius actually to in a data augmentation framework. And now I'll just show you some pictures here that experiments that Sadia did. And I think these are of course very simplistic in a two-dimensional space, but I think they to some degree kind of illustrate where these phenomenal adversarial examples might come from, right? So we have a lower dimensional manifold in a two-dimensional space. So my manifold here is one-dimensional, right? So this S shape is my one-dimensional manifold. I have blue, green, blue, green. These are the two labels, right? Blue, green, blue, green. And then the purple and red indicate the labels that the small trained radio neural network would assign. And we see in this area, so these networks, they are trained so that they actually get all the labels on the manifold correct, but here it cuts very close to the decision, to the manifold. So this would be an area where we would get adversarial loss. But if we extend with a fixed robustness radius, then either the phenomenon doesn't really change, or we start blurring the labels and lose the information. If we start extending with a kind of adaptive robustness radius, we get kind of more potentially intended behavior that the decision boundary keeps away from the manifold. Okay. More of these type of experiments. Some experiments on UCI data. What we observed is that this adaptive robust augmentation actually leads to, in all cases, best accuracy. We also proved a theorem. So this is just very initial for one nearest neighbor and under deterministic labelings. We show that this robust, adaptive robust data augmentation maintains consistency. So in summary, so what we're aiming to argue here is that the requirement for robustness should take the underlying data generation into account. Robustness should not be endowed with accuracy. And then maybe also a little bit higher level takeaways to maybe sometimes think about whether the phenomena that we observe as theorists, we like to take definition and show all kind of surprising phenomena, but sometimes these phenomena are maybe artifacts of the framework, or in this case, the loss function that we are using. Yeah, that's it.